guys, and welcome to genetics. Today's topic is we're going to learn about pedigrees. We're going to learn about the symbols and how to interpret them. Okay, so to get started, let's figure out what the symbols mean in a pedigree. The first thing is, let's do homozygous dominant for female. So that's going to be colored in. So whenever you see, so we're going to color that in. And females are always circles and males are squares. So, okay. So that's if someone has the trait and they are phenotypically dominant for it too. Okay, so then if someone is unaffected or does not phenotypically show the trait, they are just blank circles. So we're not going to color them in if they're females, and they're blank squares if they are males. And if you are a carrier, some pedigrees choose to show carriers as half-shaded individuals, because they do not show the trait, but they carry one allele for it. An allele is a version of a gene, and everyone has two alleles, one from mom and one from dad, for every gene. Although carriers sometimes, as I mentioned earlier, are sometimes shown as just blank circles. So then we'll have shade in the male. Okay, so I think now we're ready to be able to interpret a pedigree. So for our first pedigree, we're going to look at this one. So this one, now we have to decide how it is inherited. Now remember, pedigrees are not family trees. Pedigrees are used to track a trait. So an adopted child does not have to be noted in a pedigree unless they marry someone within the family or they marry within the family. And another thing we have to talk about with how to interpret a pedigree is all those lines. So first so a marriage line is the line between two individuals that is horizontal. So like this line and this line here, there's no more there. So those are all the marriage lines. But there's also children in a pedigree. So we'll highlight those blue. So all of these are the children, and they're all siblings to each other. So they're all sisters and brothers. So this particular couple, this couple here, had 4 children, 2 daughters, and 2 sons. Now you have to make sure not to get these children confused with their children, as these children have only married into the family, and they are not biologically related to individuals 1 and 2 in any way. So we have to keep that in mind. Okay, so now we can figure out if this is a dominant trait or a recessive trait. So by looking at this, we can tell that if these two individuals had a child and the trait was recessive, some of their children would have it. If he obviously does not have the trait, because otherwise he would be colored in. So let's say the trait was for rolling your tongue. So he would automatically have to be little r, little r. This individual, because they have it, they can either be heterozygous, which is one allele of each, or homozygous dominant, like so. But we don't know yet. Telling that they have a child who does not have the trait this daughter here, the only way for her not to have the trait would be to get one recessive allele from dad and one recessive allele from mom. So we know that they have to be homozygous recessive. So then this would be the genotype of the mom. So the mom is heterozygous. So dealing from that, we cannot find this individual because he has the same issue as the mom. He could have gotten one dominant allele. Oh no, we do know that because he cannot get two dominant alleles because the father does not have the dominant trait. So we know he has to be heterozygous. So the rest of their children are heterozygous. Now, if two people marry, we do not know anything about this individual because their parents are not on the pedigree. But we do know that they have a phenotypically recessive child that has to be little r. And they also have a phenotypically dominant child. But we cannot tell what this child is because, yes, we can. We can tell what this child is because of their children. If these two children are homozygous recessive, then this parent is also homozygous recessive, then this parent must have given them a recessive allele, which means that they are dominant as well. And in order for them to be, so we still can't figure out the genotype of this individual, because they could either be they're heterozygous, we decided that, sorry about that, because they gave birth to a homozygous recessive child. Now over on this side of the pedigree, we can figure out this is homozygous recessive, and this is homozygous recessive. These two, and so are these. But can we figure out, so now this is a question for you, the listener. What is the genotype of this individual? Here we go. Of this individual right here. Okay, if you said heterozygous, then you guys are right, because they cannot be homozygous dominant if both of the parents were either homozygous dominant or heterozygous. Okay, so now we can figure out that this is we had figured out that this is a dominant trait. So we can circle that. So then autosomal or sex-linked. Autosomal will be that it is carried on the first 22 pairs of chromosomes. The last pair, as you probably already know, is either XX for girls or XY for men. So usually sex-linked traits are carried on the X chromosome as it is bigger and holds more genes. We can also, an easy way to figure out if something is sex-linked is if only males or mostly males are affected by it. Here we have a mixture of both, so it will not be sex-linked, and it will be autosomal. And we have figured out the genotypes of all the individuals in this pedigree. Individual 4 has a homozygous recessive, and individual 5, this one right here, we decided has heterozygous as they give birth, as they are the parent of a recessive child. Okay, so let's try the next pedigree. So here we can see that only men are affected by this trait. So we can see there are 5 men in this pedigree. So could this be an autosomal recessive trait? Let's think about that for a minute. If it was autosomal recessive, these individuals would be homozygous recessive, but they could not give birth to this child. So the answer to this question is no. Okay, let's erase that. Okay. And then, could this be sex-linked? Let's see. So, we know that the mother has to be XX and the father has to be XY. And since traits are only carried on the X chromosome, and if it is recessive, as it is, otherwise women would be affected as well, we know that the genotype of the father has to be XRY. And now the mother, as she is not affected, but gives birth to an affected offspring, she must be a carrier for the trait. So she is heterozygous, making this son have the trait. So this is a sex-linked, or we can write X-linked to be more specific. X-linked, sorry about that, recessive. Okay, so now let's figure out the genotypes of individuals 4 and 5. Okay, so individual 4 is a female who does not have the trait, but she gives birth to 2 sons who do have the trait. So let's start with individual 5 because he is easier to figure out as he is a male and does not have the trait. So he is just like the father of his wife, as we know that they are married and that they are children, so this is as his father-in-law. Because there are only 2 options for the genotype of a male in an X-linked recessive trait. Either they don't have the trait, or they do have the trait. Okay, so then these males we know do have the trait. So then if the mother, if she does not have the trait, she has to be heterozygous for it, just like her own mother did, because it is the same thing again, as it is 2 homozygous recessive, phenotypically recessive parents give birth to an offspring who has the trait. So we know that the genotype of individual 4 is and individual 5, as he does not have the trait, is like this. So now let's try these 2 individuals. I'll give them numbers of 2 and 3 because they are the second and third members in their generation. If we were to label the generations, this would be generation 1, generation 2, this would be generation 3, generation 4, and the 5th generation. We use Roman numerals to number the generations, and we number each individual from left to right in their generation. So this would be the 1st, 2nd, and 3rd. So we're just going to focus on these 2 individuals. So we know that they come from a dad who has the trait. So we know that this dad has this genotype. And we also know that the mom does not have it. But let's see what her parents were. So we know that individual 4 was a carrier, and individual 5 did not have the trait and was not a carrier for the trait for rolling their tongue. So we can assume. So can we assume anything from this individual? Can we assume that they are either, here I'll write it over on the top of this page. So there's 2 options for them. So either they can or they can be a carrier. So can we, if we were to do the Punnett square, here I'll go to the next page. Go. If I did the Punnett square, here we go. Let's remind ourselves what their parent was. This is individual 1, 2, 3, 4, 5 in the generation. So the one parent was heterozygous, and the other one was a father who did not have it. So heterozygous and a father without the trait. And we don't even have to do this column because this column would result in sons, and we know that this individual is a female. So these are the 2, so she still has the 2 possible genotypes as we figured it out. The chances of her being one genotype of the other are greater, as she does not have any children with the trait, but she has a grandchild. We could probably assume that this is her genotype, but we cannot, so we will not label her genotype. Okay, I hope this helped you realize how to interpret a pedigree. Pedigrees. Okay, subscribe to my channel, Teen Genetics. Thanks, guys!